Here is our problem. We have the ground here, and that is going to be at the temperature of the surface, T sub S. And then we have a one-layer atmosphere, and that will be at this temperature, T sub A. Then we have black body emission from the ground that has to be transmitted through this cloud, or this layer of atmosphere, to our detector, and we'll put our detector up here. So then we also have a second term, and that is going to be the contribution from the atmosphere itself to the radiation that goes to the detector. So really, in this problem, we have two sources. We have the atmosphere emitting itself, we have the surface emitting, and in both cases, there has to be some attenuation as it goes to the detector. So what we do to model that is just to say that if we let T, with a funny little hat on it, be equal to the transmission of the atmosphere. We're dealing with a cloud-free atmosphere now, so the Schwarzschild equation is the appropriate thing to think of. Then, since we're dealing in the infrared here, we don't have to worry about Rayleigh scattering either. Then we set T equal to just e to the minus tau, where tau is going to be the optical depth. So when we have just CO2 in the atmosphere, tau is just going to be the optical depth of CO2. In general, we could have other gases. The second part of the problem, we're going to look at the situation where we have tau equal to tau CO2 absorption and emission plus tau water vapor absorption and emission. So in that case, what's going to happen, if you work through very quickly what the math would be, then we would have the total transmission of the atmosphere just equal to that due to a Beer's law form for CO2 and then a Beer's law form for the water vapor as well. Now, let's talk about the radiation model at the detector. So at the detector, the radiation that comes to it is going to be the sum of those two terms I mentioned earlier, and that is going to be so that we have a radiance as a function of wave number. So nu represents wave number here, is going to be equal to the black body emission from the surface. So we'll call that B multiplied by, or as a function of the surface temperature, and of course that's a function of the wave number as well. And then we're going to multiply by the transmission of the atmosphere, and then we're going to add to that. This is the part that is important to pay close attention to. We're going to add to it the emission from the atmosphere as well. 1 minus T is the absorption in this problem, since we don't have any scattering. So then this term here is the emissivity of the atmosphere, and we're going to multiply that by the black body function evaluated at the temperature of the atmosphere, and again that's a function of wave number 2. So this term here acts as the role of the emissivity of the atmosphere. Now let's finish up by specifying what the black body function looks like when we want to evaluate this problem. It's going to be given by B as a function of temperature. When we want to have it be a distribution function with respect to wave number, it will be equal to 2 times Planck's constant h times the speed of light to the square power. Then we're going to put in the wave number to the third power and divide by e to the hc times wave number divided by kt, and subtract off 1 from that. I'll make my units a little bit larger. Now, if we want to have this be sort of clever units, like in the problem, let's add in here times a multiplication of 100, and that will allow us to go between inverse meter and inverse centimeter units. So if we use nu in inverse centimeters in this problem, as we're calculating this, Actually, let me back that up. So let's assume in our calculation here that nu is going to be in units of inverse meters rather than inverse centimeter. Then multiplying by 100 is going to give us out in the end a black body function that is of the form with dimensions and units, watts per meter square, and per steradian per inverse centimeter. And that's the virtue of using the times 100 up there. But keep in mind that you have to put in the wave number in units of inverse meter for this relationship to hold properly. And all the other constants need to be in the metric system, MKSA, meters, kilograms, seconds, and so forth. So that should help you out with this problem. Good luck.